Alright, so after using our right hand grip rule to determine the direction of magnetic field, I can also use another thing to determine the force on a wire. If I put my wire, so this wire is carrying a current. Okay, I put it in a magnetic field, right? Okay, so this magnetic field is created by my magnets. This wire carrying current will experience a force. Okay, so why is it so? Remember, a current is just the flow of charges. So in this case, let me define that this current is a conventional current, right? So conventional current is the flow of proton. So this movement of proton will create its own magnetic field. So this magnetic field will in turn interact with the external magnetic field created by your magnet. Okay, and yeah, so that's why it will experience a force. Okay, so how do I determine the direction of the force? We can use our Fleming left hand rule. Okay, so if you need to orientate your thumb, your index finger, and your current in this particular manner. Okay, where your force is represented by your thumb, your index finger is represented by your your magnetic field is represented by your index finger, and your current is represented by your middle finger. Okay, and make sure that these three things are perpendicular to one another. Okay, yeah, so if you orientate your Fleming left hand rule, your current will be pointing in this direction. Okay, your magnetic field is pointing from north to south. Okay, then of course your thumb will be pointing in this downward direction. So this wire carrying current will move downwards. Alright. Okay, so for this wire to experience a force, first of all, the wire must carry a current. Okay, your current cannot be zero. Okay, yeah, and second, it must be perpendicular to the magnetic field. Okay, perpendicular. So if you look here, yeah, so your current is pointing from right to left, and your magnetic field is pointing down to up, right? So if you use your Fleming left hand rule, your FBI, your middle finger, okay, so middle finger is in this direction, your index finger is pointing in this direction. So your force acting on the wire will be into the paper. Okay, so this force will be into the paper. But if you have a current that is parallel to your magnetic field in the right hand side diagram, the wire will not experience any force. Okay, yeah. Okay, so next will be charged particle inside a magnetic field. Okay, so imagine that I take up a charge from the current. Okay, just one charge, be it your proton or electron, and I put it inside a magnetic field. How does it move? Okay, so first of all, this charged particle will move in circular path. Right, so this will move in circular path. And okay, so I have a proton, I put it inside a magnetic field that's pointing into the paper, and this proton is moving towards the left, represented by the white arrow. And okay, so if you use your Fleming left hand rule, FBI, right, your B is into the paper, your I is the same direction as your motion of your proton, because this I is the conventional current. So your so-called middle finger must also point towards this direction, right? And your thumb, if you orientate your your left hand correctly, your thumb will be pointing in the downward motion. Okay, so this proton will move in this particular direction. Okay, it will move in this particular direction. Alright, so what if you have an electron? Electron is negative charge, and this electron is moving in this particular direction. Right, so you have a B field that is pointing into the paper. What about your current? Yeah, remember, this current is not the flow of electron. It's not electron flow, it's the flow of conventional current. So if your electron is moving towards the left, your conventional current must be pointing towards the right. right? So you must orientate your your middle finger towards the right. And what you will notice is that your force will be pointing upwards. Okay, so your electron will move in this particular direction. Okay, move in this particular direction. Yeah. Okay. Last but not least, okay, what if you have a gamma ray? Gamma ray is something that do not have a charge. Q is equal to 0. Right. So this gamma ray, when this gamma ray travel through this magnetic field, it will not deflect at all. It will just go straight through. Okay. Yeah. So in order for the particle to experience a force, first of all, this particle must have a charge. Okay. So neutron, like for neutron, right? Neutron do not have a charge. So when I just pass it through the magnetic field, it will also not deflect at all. Okay. Second of all, the particle must be moving. It cannot be stationary. If it's stationary, it will also not experience any magnetic force. Okay, so these two criteria we need to fulfill. Alright, okay, so let's take a look at this particular. Okay, let me just reset. Okay, so okay. Okay, so you notice that we have a magnetic field. I just make it into the paper, right? Okay, and we have a positive charge, and this positive charge will move through the magnetic field. So let's see how does it move. Okay, yeah. So you notice that it's like a circular path. It's not a parabolic path. It's a circular path. Alright. So okay. So let's orientate our Fleming left-hand rule. The magnetic field is pointing into the paper. So your index finger is into the paper, and since this is a proton, right, the proton is moving from left to right. So your middle finger, which is your current, is pointing towards the right hand side. Okay, and you notice that your F, your force, your direction of your thumb is upwards. That's why your proton move in this particular direction. Okay, so let me clear the trace and see and change this charge to a negative charge. Okay, so let's see how does it move. So same thing, electron. So you point your index finger into the paper, and since this is a negative charge, right, so our eye must be pointing towards the left hand side. Okay, and your thumb will be downwards. So that's why your negative charge move in such a particular direction. Right? So this is for the particles inside your magnetic field.